lecture 2, where we saw the bias mitigation. Actually, why I have started this gender and diversity policy in AI, or practically the AI policy or regulation, how to do it and what policy means and what are the regulation needed, why needed, where AI can do harm. So I wanted to do this basically to share the knowledge with as many people as possible. This AI regulation has suddenly came, and what I feel like we do not have enough knowledge among the people, both across. A lot of people are building AI system, a lot of people are learning it. But then you can build a system, but if that system has not received the license to be used, then building the system will have no use, and the company who are going to build it is not going to make any commercial value out of it. And as a result, the company who will put money to build the system, they will go bankrupt and they will close down, because if you cannot make money, the company will go away. So what I feel that there are a very high number of skills requirement in the AI community, where the student know this AI regulation and what are the tricks and tips, what to consider and what not to consider, and where to focus and how to design an AI system which has mitigated biasness and can adhere to the compliance of AI Act. Right now, the AI Act is in the European Union, so anything you are developing in EU or selling in EU to be used has to follow EU compliance. Anything you are developing outside European Union and which has an AI integrated in the system, and you are selling into the Europe, then that must follow the AI compliance. So if you say that it doesn't concern you, it is European AI Act, but it does concern you because you are building a system, and if Europe is your market, then you have to follow the AI compliance, and what you are building need to adhere to the AI compliance. So this knowledge is going to be moving forward one of the very basic necessity of an IT company or AI company who are building the system. It's very much similar to you are learning software engineering, the people who are making software, but this UAI Act will matter across. Even if you are an organization who is going to buy an AI system, you are not building an AI system. You are not a technical person. You are not from a computer science. You are not from engineering background. You are from a policy side, or you are from the HR side. You are from anyone in an organization who are going to buy the AI system to be used into the organization must know this. So enough of the talk, why we need to learn it. As a teacher, we start becoming more preaching kind of person. So please excuse me. So welcome back, student. My name is Dilip Prasad, and I am going to take you through this visual walkthrough of this Jupyter notebook for lecture 3. So in this notebook, we will, by programmatic way and by seeing how the mitigation of different biasness look like, I mean, how the programmatically it can be implemented. And I have taken a very simple example. When you are working in a company, you will have a complex example, but this concept will be transferred. Like false positive rate is a false positive rate, whether you are doing for simple data or you are doing for complex data. Statistical parity difference is a statistical parity difference. So that's how it is. So my washing machine is making a noise that your clothes have dried up, and I can see it is 4:40 a.m. in the morning, and I am recording this lecture. So welcome back. Now, in this, I will walk you through the this bias mitigation technique in AI. So in the theoretical lecture, in the lecture 3, we saw, so in this, we will see how to mitigate the biasness of different types in an AI model. So What this notebook is going to cover. If you don't know how to run the Jupyter notebook, so you can follow my previous hands-on where I have shown that how to upload the Jupyter notebooks. And this notebook code is going to be, the link will be provided in the description. So in this, what we are going to take, that's very visual and synthetic examples and very simple experiment to see why imbalance in the data set create unfair behavior, and what is the how the oversampling or undersampling during the training time affect, or the oversampling from a particular group or undersampling from the other particular group during the training affect the model behavior. And we will take a baseline model, and then we will do the balancing of the data and see how the performance goes on, and then simple post processing example using the threshold adjustment, how we can mitigate some of the biases or some of the effective biases. And then we will take you through the mitigation technical mitigation. We will see that even by doing the mitigation, not all the time everything can be mitigated. And then why the designing the AI system right from the beginning, which is inclusive and supporting diversity, is needed. Many times after doing the training or after collecting the data, mitigating the biasness is not always possible. So the bias mitigation. Now, bias mitigation, just to recap, that is not a one technique or one trick. Just like there are different types of biasness are there, like in my book, more than 33 different types of biases have been mentioned. So to recorrect those biases, very much like there are 33 different kind of diseases, you need 33 different kind of medicine. So if you have 33 different kind of biasness, you need at least more than one type of bias mitigation technique to counter those 33 biasness. Now, in practice, uh, the bias mitigation can be done before training, means when we are pre-processing the data, and it can be done during the training time while in processing happening, and once the model has been trained. Then also there are some techniques are there, which is we can use it after the post processing to mitigate the bias. But now best way is design the whole system while doing the bias mitigation. So that is the fourth and the best way. But often we join a company where everything has been trained and we just have a model, and your boss says that, okay, do the bias mitigation because now we have to sell the system to you and you has a compliance to maintain. So many times the data has been captured long time ago. We cannot go back and collect the data. So different scenario, different kind of approach can be done. But best possible way is while doing the system, designing the system, we can address the biasness. That is the best possible way. So now we see in this, you have the import. I'm just calling the four libraries: NumPy libraries, Panda libraries, Matplotlib, and Seaborn. And then the fifth library, scikit-learn. So it is a machine learning library for using many kind of machine learning functions are already been included. And I am taking the random seed, and here I'm creating a synthetic data set. You see, I'm creating a synthetic data set. And in that hiring AI example, I have taken that an AI system is there, which is helping in uh, recommendation of the CV. Now, I've taken the two group A. I purposefully make the data imbalance just to show the impact. So where group A is, so in your AI system has received two types of group application. One group has more data and others have less data. So, and it can happen in real scenario also. So what has been done, you can see that one group had 900 example and other had uh, lower number of examples. Okay, 180, and here 900 are there. 100 and 900. Okay. Now I see. the resetting the data to 0, and then score has been defined for different group, and experiment random data has been taken, and different metric has been then other function has been done, and here logit function has been applied, and you can see the data when we visualize it, 5 data. We see that the scores and experience of the candidate and selected, not selected is already pre-populated. Okay. Now, if we visualize this data, you can see I'm putting up plot function, plot.figure, and you can see that as I have taken 900 samples on a group A and 100 in a group B, so this data is currently imbalanced. And in real scenario, this could be also the case. So what we see that group A has number of candidates selected from group A is 56% and other had 45%. Okay. What to note here is that one group appear much less often in the training data, and model might not have learned from enough from that group. So group B has less data. So probably it has not been enough learned. So that's the group which has more data. We have oversampled data, and the group we have a less data, we have undersampled data. So some of the data it has not learned. So let's see the what happened when data is not balanced and after we balance the data set. So I take an example where an oversample data set is there, and then after take an undersample data set. So in this, what I'm showing that, I make the bigger. So in this, what I'm showing that I'm trying to take oversample data from minority group, and then I'm undersampled to make a majority group. And then with this small programming example, so before balancing, the data was 900 by 100. But after balancing by oversampling group B, I created 900 in the group B as well. There are many ways to oversample it. And then if I do undersampling, where I have taken 180 data from group A and 180 data from group B. So group B had 180 data here. Okay. Yeah, so 180 and 180 I kept. So I clipped group A data to only 180 data has been chosen. Now, if we oversample, we increase the example from the underrepresented group, and undersampling by reducing example from the overrepresented group. So this method can improve the result representation, but it comes with some trade-offs. Like if we oversample it, then we are increasing overfitting. That model will be overtrained, and it will overtrain because of towards the direction where the data is more, and it will, when the new kind of data comes and the model have not seen that kind of data, then it start performing poorly. Now, if you do undersampling, then also we have removed information by undersampling. So some useful information can go away. It can happen that once, let's say we remove some sample and few samples which were responsible for AI to learn, they get removed. So as a result, for group B or that undersample group, the model will not learn enough and it will start performing poorly. Now, what we are doing here is that we are taking a simple machine learning, simple logistic regression model is prediction model we are building on the original imbalance dataset. So this is the original dataset. And you can see the test size we are taking 35, and then random state we are choosing 42. Method we are choosing stratify training method we have chosen. And in this, we call this function called logistic regression. This is a scikit-learn library function. And in this, we are running for 1000 iteration. So this baseline model we are building, and we are passing here the data X train and Y train. So Y train has the labels and X train is the data we are passing. And then after this baseline model dot fit is going to do the training. Okay. And once it does the training, we will get the data in the output. And what we see that accuracy of this model is 75%. Okay. Now, what we see, what can we calculate is that what are the different group fairness metrics are there. We can compare them with some easy metrics. What is a selection rate? Means percentage of predicted, what has been predicted. How many of them predicted results are positive? So percentage predicted positive, that is how much we have selection from each group, selection rate from each group. Now true positive rate, so among truly qualified cases, how many we have correctly identified, means those who are supposed to be, they meet the criteria, and among them, let's say if 80 were from the qualified numbers out of 900, how many from 80 we have actually able to correctly identify this model. Then positive prediction value, when the model predict positive, how often it is going to be correct. If it say I have selected the candidate, how often it is going to be predicting correct one. So with this, we can calculate statistical parity difference like thinking that compare the selection rate, EOD like thinking, compare the true positive rate across the group, and purchase positive parity difference like thinking, compare the positive predictive value across the two groups. If you have more than two groups in your data set, then across those groups. So as per EU/AI Act, if your system is high-risk system, then you have to do the subgroup biasness metric calculation. So we can see that group metrics are there, and then we are just appending the data there, and here calculation is happening. True positive, PPV, FPR are getting calculated here. I'm not going to the detail how the model is doing machine learning. It is not a machine learning lecture, so I'm not going through. It is an AI policy, so I'm assuming that this has been calculated and how the biasness and mitigation can be done. So we see Group A, the selection rate was 56%, and Group B selection rate was 56.3%, more or less closer. Now, true positive rate of Group A was 79, while true positive in Group B was 83. So we see the difference, and there were 307 count was from Group A and then 71 from Group B. So as you know that this was the unbalanced data set. Now, when we see the comparison that the baseline model, how the selection rate across different groups are there. So a selection rate for Group A and Group B is more or less closer, but in true positive rate, Group B is higher. So this some differences there, but not a lot of difference. Now, the interpretation, what we can see from this chart, that one model can look different depending on which fairness question we ask. So if you say that selection rate, they look okay. But now if we say that true positive rate, then Group B has a better true positive rate for the same model. So what does it mean that different fairness metric capture different ideas of fairness? So do remember that what we are measuring. Now we are doing oversampling example, that now we will train the same model after balancing the training data by oversampling the Group B. Means we increase the number of data for Group B by just repeating, or there are different ways are there. Now, what we did, we created the data, training the sample B we have oversampled by this function, train over. And then we are calling this same logistic regression machine learning approach. And for same 1000 iteration, and then we are calling this training and passing this training data. And then after that, we're calculating the metrics. So we see that compared to the previously, the metric to positive rate, etc., has changed after oversampling. So later we see the comparison. Okay. So here we are creating the comparison with when uh, we had the uh, selection rate when we were having the not balanced the data. So selection rate were like this. Now we oversample the group B and we can see the selection rate actually gone down for both. Uh, and we can see the selection rate has gone down for both. Now for true positive rate, we can see that the compared to the baseline, we had this kind of small differences. Now, after oversampling, the differences have slightly increased with the group A and group A, group A and group B. Now, among the PPV, we see that after oversampling, we do see small differences in the baseline and not the baseline. Sorry, going away. This baseline and not the baseline. Excuse me. So you can see between that. So what points we want to note that here is that oversampling can help the model that to add examples from underrepresented group. But we see that in this, we simply duplicated the example. So as a result, what we saw that overfitting for group B model prediction is happening because we simply repeated 180, 180, 180, 180, we repeated until the equal to the group A numbers. Now let's do the undersampling of group A and try to match the number of sample of group A with the group B. So in this same group A sample has been undersampled and we have removed the sample from there to just match it with the group B. And same logistic regression model for 1000 iteration has been called, and we are training here in this place. This call is for training. Now, what we see that some difference is happening after undersampling of a group A. And then if you want to compare, you can see the with the baseline for oversampling and undersampling, we see that for baseline when it was unbalanced data, it was closer for selection rate. Oversample, overfitting has happened. Undersample, we see that performance of group A slightly started reducing because we removed the data from group A. Similarly, if we do the baseline for this true positive rate, there also we see the difference have increased when we have done undersampling. So some important information going away. And same we will see for PPBB, information. So there are differences are there. So once now what we see comparing the three models. So I plotted these three models in one place. So you can see in a nutshell. So we can see in a nutshell that how the performance varies for selection rate, true positive rate, and PPB when we are taking an imbalanced data set and then we are using oversampled approach to bias mitigation and undersample approach for bias mitigation, then we saw the difference. So this you can see that we did some mitigation, but with a trade-off. Now we combine the fairness metric for these particular samples. We see the metrics are like this. Now, what point to note here is that undersampling can make groups more balanced, but it can throw away important information from the group where we have removed the data. So a simpler data set is not always a better data set. Okay, that we have a balanced data set, or simply remove the data for undersampling, or duplicate the data for oversampling. Now there are approach like some post-processing, that your model has been trained and now we will use some threshold adjustment. How does it mitigate some of the bias? That we keep the model fixed. We are only going to change the threshold for decision of the model for, let's say, internal of the AI model. There are some values model gets at the outside. And if we are doing a classification, and let's say two groups are there, group N and group B. So in the last layers of the AI model, there will be score, and sum of those score for each input will be equal to 1. So what we typically do, that let's say threshold 0.8 and above, if it belongs to a particular group, then the prediction will be for that group. So now we can adjust the threshold. If we can make it 0.7, 0.6, so that threshold adjustment we are doing here. So for pre-processing, which changes the data, and after the pre-processing, post-processing, which changes the decision rule. Okay. So what we see here, true positive rate, PPB, false positive rate are given here. And after that, what we are trying to see, different kind of threshold we are putting. So here a threshold is there, 0.4 to 0.6. So by putting different kind of threshold, we can see the bias mitigation is happening post-processing way. And similarly for true positive rate, also some changes we see, and we will see the for PPB as well. We'll see for the PPB as well. Some changes there in the PPB also, you can see. Now, so here the decision threshold has been chosen. Now what to be noted here, that by changing the threshold, we can change the fairness related outcome without retraining the model. We are not retraining the model. We have the pre-trained model, but we are just changing the decision boundaries. And what we are doing is post-processing after model has been trained. So we thus do some changes, thus do some managing some kind of biasness it can overcome. But what happened that this particular parameter change we are doing at the model level. Now this adjustment are not transferring to the users. Or second thing is that once you have imported a model from for work to the Europe, which are trained elsewhere, and we are changing this decision boundary. Now question comes, is it legally or ethically acceptable in a different kind of domain? Medical domain, definitely not acceptable. So then if you do it, then you have to go for compliance. You have to do the compliance process again. Now, question also is there, does it improves one type of fairness metric while version the other kind of fairness metric? Now, this lead to the information that we can see that if we do pre-processing, means pre-processing bias mitigation, means data, we do the data level bias mitigation before the training. Approaches are oversampling, undersampling, and reweighting is there. The what data, which data I have given more importance, weighing is there. Then during the training process, we can use different kind of learning approach, which mitigate different types of biasness. So we can use a learning approach, which are fairness aware, objective function, or putting some constraint. Now, once model has been trained, then before doing the final prediction, we can do the threshold adjustment, or we can also do the calibration of the system for getting the different, mitigating the bias. So what I want to say here is that different kind of interventions are there, pre-processing, in processing, and post-processing, and to target different kind of unfairness and its sources. What we are trying to do is that we are using some technical fixes here, but which is at the data level, model level, and after the model has been trained. But it is not always sufficient. Like if we are doing training data, might can miss important community. We have not taken all type of diverse group data. Now, the team which is training the model or collecting the data, or that team does not have diversity, so they may overlook the inclusive and fairness of the system design. And this system which we are building may be inaccessible to some of the users, and after the deployment, it is creating new type of harm which was not being addressed during the or known during the training time. So this is why the inclusive and diverse AI system at the system design level is important for bias mitigation. Now we see here different kind of categories, representation of different groups, accessibility and transparency and participation, culture fit. So now I have just given the example. I have taken the synthetic example, like I have given the value 212121 and improved score 444. So this is just random example has been taken to explain the concept. And with that, I show you that if we do the weak design, if we do the weak design, then the representation was not good. But if we have the inclusive design, the representation became the group. So this is, I have put the data to show that how the inclusive system design different metric can improve by if you have included inclusive and diverse system while designing the AI system. The whole inclusivity and diversity has been integrated while building the system. So, and this will also help making the system, even after deployment, monitoring time also is going to have a better performance. Now, what are the practical checklist for a fairer AI is there? We need to think that, is the data representative? Do we have the data which we are using for AI training represent the targeted groups? Have we included all the group, or we have missed some groups for which the system is going to use? That is before the training, data collection time. Now, during the training, is the model only optimizing for accuracy? Is it also fairness aware, or we have added the fairness constraint during the training time? And after the training, if you see that outcome is fair across different kind of groups, or do we have a different fairness metric telling the different kind of stories? Now, once we have deployed the system, we need to see that which type of groups has been excluded, because that time during the deployment time, if a data comes or people are using which doesn't belong to a particular group in the training data, then the system start behaving differently. And is the system accessible and understandable? Is the system is continuously auditing even the deployment process? So the need to know that bias mitigation can happen before making the AI training, during the AI training, and after the training. Oversampling, undersamplings are useful method, but they also have limitation. We can do the threshold changing after the model has been trained, which can change fairness outcomes. There are no technical fixes which can solve all types of biasness problem. There are multiple types of approach need to be done. And if you want to make a fairer AI, we need to start thinking inclusivity and diversity while building the system. Not everything has been done, data has been collected, training has been done. So if data has been collected and we just have to build the system, biasness will be there. So inclusivity and diversity has to be included even when before we are going to build the system or collect the data. So with this, I will take the final note that every mitigation method will solve part of the biasness problem, but it is not going to solve the whole problem, because if you have a different kind of disease, we need a different kind of medicine. So if you have a different kind of fairness problem or biasness problem, we will need a different kind of mitigation approach to solve the whole problem. One approach will not solve all the problem.